When you look up into the vast clear darkness of the night sky, what do you truly see? You see points of light, stars, planets, and if you are far from the city, a faint milky smudge that our ancestors called a river of heaven, our own galaxy, the Milky Way. For all of human history, we have equated the universe with this light. Astronomy was by its very definition the study of light. We built our telescopes to gather it, our theories to explain it, and our sense of the cosmos on the fundamental assumption that what we see is what is there. But what if this assumption, the very bedrock of our cosmic understanding, is completely wrong? What if the universe is not defined by the brilliant shining objects that clamour for our attention, but by an immense invisible presence that quietly shapes everything? What if the grand motions of the galaxies, the elegant spin of the spirals, and the very architecture of the cosmos are just a dance choreographed by a partner we cannot see, touch, or comprehend? This is not just a philosophical thought experiment. It is the starting point of the single greatest mystery in modern science. It is the chilling and profound realization that everything we know, every star, every planet, and every atom in our bodies might be nothing more than the shimmering foam on the surface of an unfathomably deep, dark ocean. The first whispers of this mystery came not from some exotic distant object, but from something astronomers thought they understood well: the spiral galaxy. These are the pinwheels of the cosmos. We see them everywhere, massive islands of stars, dust and gas spinning gracefully in the void. And because we live in a solar system, we felt we had a perfect model for how they should work. Think about our own solar system. At the center is the sun. The sun is the boss. It contains over 99% of all the mass in the entire system. Because of its immense gravity, it dictates the speed of everything that orbits it. Mercury, which is very close, is gripped by an intense gravitational pull and has to move incredibly fast, about 48 kilometers per second, to avoid falling in. Earth further out moves at a more leisurely 30 kilometers per second. And Pluto, way out in the cold darkness, barely feels the sun's pull at all and crawls along at less than 5 kilometers per second. This is a fundamental rule of gravity first observed by Johannes Kepler and explained by Isaac Newton. The farther you get from the central mass, the weaker the gravitational pull, and therefore the slower you must move to maintain a stable orbit. This is called a Keplerian drop-off. It's elegant, predictable, and it works perfectly. So in the 1960s and 1970s, astronomers like Vera Rubin and Kent Ford turned their powerful telescopes toward our neighbouring spiral galaxies like Andromeda. They wanted to map their rotation. The logic was simple, just like our solar system. A spiral galaxy has a bright, dense core or bulge. You can see it with your own eyes. That central bulge contains the highest concentration of stars, and therefore it should contain the vast majority of the galaxy's mass. The expectation was clear. The stars near the bright center would be moving very fast, and the stars on the far outer edges of the spiral, far from that central mass, should be moving very, very slowly. Their speed should drop off just like Pluto's. They did not. What Vera Rubin and her colleagues found was so strange, so impossible, that it was initially dismissed. They measured the speeds of the stars at the center. They measured the speeds of the stars in the middle of the arms, and then they measured the speeds of the stars and gas clouds at the extreme faint outer edges of the galaxy. Instead of slowing down, the stars on the very edge were moving just as fast as the stars much closer in. Some were moving even faster. If you were to plot this on a graph, the expected speed would go up and then fall off dramatically. The observed speed went up and then just stayed flat. It extended from the center to the farthest visible point. This graph is now one of the most famous and troubling charts in all of science. It is known as the flat rotation curve. This discovery was a crisis. It was as if we looked at our solar system and found that Pluto was orbiting the Sun at the same speed as Mercury. It meant one of two things: either our entire understanding of gravity, the laws of Newton and Einstein, was fundamentally wrong, or the galaxy was hiding a secret. It meant that the rules of gravity were working, but we had massively miscalculated the mass. Think of it this way. If you are swinging a heavy ball on the end of a thin string, you can only swing it so fast before the string snaps. If you want to swing it faster, you need a stronger, thicker rope. The gravity from all the visible stars in the galaxy was the thin string. The speeds of the outer stars were far too fast. They should have been flung off into the darkness of intergalactic space, the entire galaxy tearing itself apart. But they weren't. They were being held in their orbits. This meant there had to be a thicker rope. There had to be an enormous unseen source of gravity, a truly colossal amount of mass holding the entire galaxy together. This was the first undeniable clue, a clear message whispered by the spinning spirals. You are not seeing most of what is here. This invisible something needed a name. Scientists, in a moment of humble honesty, called it dark matter. It is dark because it does not interact with light in any way we can measure. It does not shine, it does not reflect light, and it does not block light. It is utterly perfectly transparent, and it is matter because it has mass, and because it has mass, it has gravity. And where is this dark matter? The flat rotation curves gave us the answer. It's not just sprinkled among the stars. The calculations showed that the visible part of the galaxy, the beautiful spinning pinwheel of stars and gas, is only the very centre of a much, much larger structure. The visible galaxy, it turns out, is embedded within a gigantic spherical halo of this invisible dark matter. Imagine the spiral disk we see as a glowing vinyl record. Now imagine that record is floating inside a massive invisible beach ball that extends far beyond the record's edge in every direction. That invisible ball is the dark matter halo. This halo is the true master of the galaxy. It is this invisible scaffolding that provides the vast majority of the gravity in its mass is what dictates the speed of the stars. The bright visible galaxy we love is just the decoration. It's the visible tip of the iceberg, while the true bulk of the cosmic structure remains hidden cold and dark. This discovery didn't just add a new object to the cosmic inventory, it fundamentally changed the recipe of the universe itself. When the first clues about the missing mass began to pile up, the scientific community did what any sensible person would do. They looked for the most obvious answer. This is the lost keys principle. If you lose your keys in your house, you don't immediately assume a ghost teleported them to another dimension. You check your pockets, you look under the couch cushions, you check the kitchen counter. You look for the normal, everyday, boring explanation first. In cosmology, the lost keys were the mountains of missing gravity. The obvious explanation was that the universe was simply filled with a lot of normal, everyday matter that was just hard to see. After all, the universe is a very dark place. Maybe it was just full of stuff that didn't shine. This normal stuff has a specific name, baryonic matter. This is just a scientific word for the things we are all made of: protons and neutrons and the electrons that go with them. Stars, planets, people, computers, and even vast clouds of hydrogen gas are all baryonic. So the first great hunt began. Scientists set out to find all the dark baryonic matter. The list of suspects was long, and collectively they were given a brilliant nickname, MACOs, which stands for Massive Astrophysical Compact Halo Objects. This name was a direct playful challenge to the other leading theory, which proposed new exotic particles called WIMPs, weakly interacting massive particles. The battle was on with the missing keys under the couch, MACOs, or had a ghost really taken them WIMPs? The MACO suspects included vast clouds of cold gas and dust. While we see some gas clouds, maybe the galaxy's halo, that big spherical region around the spinning disk, was full of gigantic freezing cold clouds of hydrogen that just don't glow. Failed stars, brown dwarfs. These are objects that tried to become stars but failed. They are much bigger than Jupiter, but not quite big enough to ignite nuclear fusion in their cores. They are incredibly dim, glowing only faintly from their own internal heat. Dead stars. What happens when a star dies? It can become a white dwarf, a neutron star, or a black hole. White dwarfs and neutron stars are small, dense, and cool over billions of years until they are almost impossible to see. Stellar mass black holes are by definition completely dark. Rogue planets. Trillions of planets that were kicked out of their own solar systems and now wander the dark, empty space between the stars, forever cold and alone. This list seemed very promising. Surely if you added up all these dark but normal objects, you could find the missing mass. The problem was, how do you search for things that are invisible? You can't take a picture of them, but you can watch for their gravity. Albert Einstein's theory of general relativity tells us that a massive object bends the fabric of space-time. Light follows this bent path. So a massive object, even an invisible one, can act like a lens. If a dark massive object like a MACO passes exactly in front of a distant bright star, its gravity will bend the light from that star and focus it toward us. This effect is called gravitational microlensing. From our viewpoint on Earth, it looks like the background star suddenly and smoothly gets brighter, and then as the MACO moves away, it fades back to normal. The pattern of this brightening is unique. It's perfectly symmetrical, and it happens at all wavelengths of light at the same time. It's like a cosmic magnifying glass passing by. This gave astronomers a brilliant and incredibly difficult search strategy. They would pick a patch of sky with millions of stars like the Large Magellanic Cloud, a small neighbouring galaxy, and take pictures of it every single night for years. Several teams, including the Macho Project and the Ogle Optical Gravitational Lensing Experiment Survey, did exactly this. They programmed computers to scan the brightness of tens of millions of individual stars night after night, looking for that 1 in a million telltale brightening event. The search was a stunning technological achievement, and they found them. They did detect microlensing events. This was a victory. It proved for the first time that the dark halo of our galaxy does contain these dark machos. Brown dwarfs, rogue planets, and old white dwarfs are really out there wandering in the dark. The lost keys were under the couch just as predicted. But then came the devastating blow. While they found some events, they didn't find nearly enough. The scientists did the math. They calculated, if all the missing dark matter was made of machos, we should have seen, for example, 500 microlensing events. They had only seen about 50. The numbers were clear, and the conclusion was inescapable. Yes, machos exist. Yes, they add to the total mass of the galaxy, but they are just a tiny fraction of what is missing. They are the loose change in the couch, not the lost keys. They could account for maybe 10% of the missing mass at the most generous estimate, but that left 90% of the problem completely unsolved. This is what shifted the entire field of cosmology. The result of the macho search was one of the most important negative results in the history of science. By trying so hard to find the normal answer, scientists had proven beyond a reasonable doubt that the normal answer was wrong. This brings us to the true terrifying scale of the problem. Take all the matter we know, the stars, the gas, the dust, the planets, and even the dark machos we just hunted for. Add it all together. This is the baryonic matter. Now look at the total amount of gravity we measure. The amount of gravity is 5 to 10 times greater than what all of our normal baryonic matter can produce. Let that sink in. For every pound of stuff you mean, the Earth and the Sun are made of, the universe has over 5 pounds of an invisible unknown something else. This something else cannot be baryonic. It's not made of protons and neutrons. It is something fundamentally different from us. It doesn't interact with light at all, it doesn't glow, it doesn't reflect, it doesn't even cast a shadow. It is a completely new kind of substance, a ghostly material that makes up the vast majority of all matter in the cosmos. The hunt for the normal stuff was over. It had failed, and in its failure it gave us the most profound clue of all. The missing mass was not just dark, it was dark matter. The real hunt, the hunt for a new exotic particle that shapes the universe, was just beginning. The evidence from the motions of galaxies is compelling. It's what first forced us to consider that the universe is hiding its true weight. But in science, one piece of evidence is a clue. 2 or 3 from completely different sources starts to look like a conclusion. The second and perhaps most profound line of evidence doesn't come from tracking motion. It comes from Albert Einstein and his revolutionary description of gravity itself. Before Einstein, we thought of gravity as a pull, an invisible rope connecting 2 objects. But Einstein, in his general theory of relativity, gave us a new image. He said gravity is not a force, but a consequence of matter and energy warping and curving the very fabric of reality, the 4-dimensional thing we call space-time. The classic analogy is a bowling ball placed on a trampoline. The heavy ball creates a dipper curve in the fabric. A marble rolled nearby won't fall toward the bowling ball because of a pull. It falls toward it because it's following the straightest possible path on a curved surface. This was a radical idea, and it made a strange prediction. If massive objects curve space, then they should even bend the path of light. Light always tries to travel in a straight line, but if the straight line itself, the fabric of space, is warped, the light will follow that curve. This wasn't just a theory. In 1919, Arthur Eddington famously observed a solar eclipse. He saw that the stars behind the sun, from our perspective, appeared to be in the wrong place. Their light passing by the sun's immense gravity had been bent. Einstein was right. Now let's take that idea and we'll scale it up. Instead of the sun, imagine an entire cluster of galaxies. A galaxy cluster is one of the most massive structures in the universe, a city of thousands of galaxies all bound together by gravity, containing a total mass of quadrillions of suns. The dip this cluster makes in space-time isn't a dip, it's a canyon. If we look at a distant galaxy that happens to be behind this cluster, its light has to travel to us through that canyon. As it does, the light is bent and redirected. From our perspective on Earth, the cluster acts like a giant cosmic magnifying glass. This effect is called gravitational lensing. When our most powerful telescopes, like the Hubble Space Telescope, stare at these massive clusters, we see this effect in breathtaking detail. The distant background galaxies are smeared, stretched and distorted into long, thin arcs of light. It looks like the universe is being viewed through the shimmering curved base of a wine glass. Sometimes, if the alignment is perfect, the background galaxy is smeared into a complete circle known as an Einstein ring. This distortion is more than just a beautiful curiosity. It is a tool. It is a cosmic scale. The amount of distortion we see, how much those background galaxies are stretched, is directly related to the amount of mass in the foreground cluster. More mass means a deeper curve in space-time, which means a more extreme bending of light. So astronomers can use this. They can weigh the cluster just by looking at the pictures of the warped galaxies behind it. And this is where the second independent proof comes from. Astronomers did this calculation. They measured the lensing and calculated the total mass of the cluster. Then they did it the old-fashioned way. They counted up all the visible stuff. They counted the stars in the thousands of galaxies. They measured the enormous clouds of hot gas that float between the galaxies, which we can see in X-ray light. They added it all up. All the stars, all the gas, all the dust, everything we can see. The numbers didn't match. They weren't even close. The mass that the visible stuff accounted for was once again only about 15% of the total mass. The lensing, the bending of light, revealed that the cluster was 5 or 6 times heavier than it should have been. This was the same result, the same missing 5-to-1 ratio that Vera Rubin had found by watching galaxies spin. One method used motion, this one used light. Both told the exact same story. The vast majority of the matter in the universe is invisible. But even with this, a skeptic could still have a reasonable doubt. Maybe they might say we don't need dark matter. Maybe Einstein's theory of gravity is just wrong on these enormous cosmic scales. It's a fair point. How do you prove that the problem is missing stuff and not just a misunderstood rule? To answer that, the universe gave us a gift, a smoking gun. It's an object known as the bullet cluster. The bullet cluster is not a single quiet cluster of galaxies. It is the site of a cosmic cataclysm. It is the in-progress high-speed collision of 2 entire galaxy clusters. About 50 million years ago, these 2 massive clusters, drawn together by their own immense gravity, smashed into each other at millions of miles per hour. This is without exaggeration one of the most violent and energetic events to have happened in the universe since the Big Bang. And it provided the perfect natural experiment. Let's think about what happens in a collision like this. These clusters are made of 2 main things: normal matter, mostly in the form of a gigantic superheated cloud of hydrogen gas that floats between the galaxies. This gas cloud is actually more massive than all the stars in the cluster combined. Dark matter. This is the invisible stuff we're trying to prove exists. When the 2 clusters collided, what happened to the normal matter, the gas? It did what gas does. It smashed into itself. Like 2 giant waves crashing, the gas clouds collided, creating a massive shockwave. They compressed, heated up to millions of degrees and slowed down, getting stuck in the middle. When gas gets that hot, it shines brilliantly in X-rays. So when our X-ray satellites look at the bullet cluster, they see a bright glowing bullet-shaped blob of gas right in the center. This is the wreckage of the normal matter. It's where almost all the stuff that makes up us is located. But what about the dark matter? The theory of dark matter says that it doesn't interact with, well, anything. It doesn't interact with normal matter, and it doesn't even interact with itself except through gravity. It's collisionless. So the prediction was this. When the 2 clusters collided, the gas clouds would smash together and stop. But the 2 giant invisible clouds of dark matter should have just passed right through each other, like 2 ghosts flying through a wall. This means that in the bullet cluster, the normal matter, the gas should be in one place, the middle, and the dark matter should be in 2 other places on the sides having passed through. How could we possibly test this? Gravitational lensing. We can use the distortion of background galaxies to map where the mass is. Forget the X-rays, forget the stars, just where's the gravity? So astronomers did it. They created a map of the mass by looking at the lensing. What they found was one of the most important discoveries in the history of cosmology. The map of the mass did not match the map of the gas. The X-ray telescopes showed the normal matter, the gas, as a single glowing blob in the center. But the gravitational lensing map showed 2 massive invisible clouds. One was on the far left of the collision and one was on the far right. They had passed right through the center completely unfazed. The mass, the gravity, was in a completely different place than the matter we could see. This was the smoking gun. It was a direct visual separation of normal matter from dark matter. It told us in no uncertain terms that gravity is not just behaving weirdly. If it were, the gravity would have stayed with the gas where all the normal matter was. But it didn't. The gravity, and thus the mass, had moved on. The bullet cluster shows us that the universe is unequivocally composed of 2 different kinds of substances. There is the familiar stuff that collides and glows and makes up our world. And then there is this other dominant invisible substance, a silent scaffold that holds the cosmos together, interacting only through the gentle, persistent pull of gravity. The temperature of a ghost. To build a portrait of our invisible culprit, we can't use a photograph. Instead, we have to deduce its properties like a detective sketching a suspect based on their actions. We know dark matter doesn't interact with light, but its most important property, the one that shapes the entire universe, is what cosmologists call its temperature. This is one of the most confusing terms in physics because it has almost nothing to do with feeling hot or cold. In cosmology, temperature is a code word for speed. Hot, dark matter. HDM refers to particles that are relativistic, meaning they move at or very near the speed of light. Cold, dark matter. CDM refers to particles that are non-relativistic, meaning they move slowly. At least they were moving slowly at the time when the universe began to form structures. This single distinction, fast versus slow, is the most critical clue we have because it completely changes how a universe would be built. The case against hot. For a long time, we had a perfect candidate for hot dark matter, the neutrino. Neutrinos are real particles that are part of our known physics. They're incredibly mysterious. They are produced in stars and nuclear reactions. They have a very, very tiny amount of mass, and they pass through almost all regular matter as if it weren't even there. Trillions of neutrinos are passing through your body right now and you'll never feel them. They are dark and they have matter. They seemed perfect, but there was a fatal problem. Because neutrinos are so light, they are born moving at nearly the speed of light. They are fundamentally hot. Now imagine trying to build the universe with these hot particles. In the very early universe, matter wasn't perfectly smooth. There were tiny random patches that were just a fraction denser than other patches. Gravity wants to pull these dense patches together to make them even denser. This is the seed of a future galaxy. But if your dark matter is hot, its particles are moving far too fast. As gravity tries to pull a small clump together, the hot particles just zip right out of it. Their own speed and energy easily overpower the weak pull of gravity from a small seed. This process is called free streaming. The hot particles effectively stream free from any small gravitational clump, wiping the slate clean and smoothing out all the small-scale differences. In a universe dominated by hot dark matter, you simply cannot form small structures. The only things that could possibly form are unimaginably huge cosmic-scale structures, first like giant filaments or pancakes of matter hundreds of millions of light-years across. Only on these enormous scales would the combined gravity be strong enough to finally trap the speedy hot particles. In this hot dark matter model, these giant superstructures would have formed first, and then much later they would have fragmented into smaller pieces like galaxies. This is known as a top-down model of structure formation. The evidence for cold, the top-down model, makes a clear prediction, but when astronomers pointed their telescopes like the Hubble Space Telescope at the deep universe, they saw the exact opposite. They didn't see giant structures breaking down, they saw small things building up. The universe we observe is built from the bottom up. Gravity first pulled together small, manageable clumps of dark matter. Because this matter was cold, moving slowly, it couldn't escape. It settled into small, dense, invisible halos. These small, cold dark matter halos acted as the gravitational seeds for everything else. They were the invisible scaffolding of the cosmos. Regular matter, the hydrogen and helium gas of the early universe, was then pulled by gravity into these dark matter halos. Once inside, this gas could cool, condense, and ignite into the very first stars and the first small dwarf galaxies. Over billions of years, these small dwarf galaxies, each wrapped in its own dark matter halo, were pulled together by gravity. They crashed and merged again and again in a grand cosmic demolition derby, building up larger and larger structures. Our own Milky Way galaxy is a product of this bottom-up assembly. In fact, we can still see it happening. The Milky Way is currently in the process of eating several smaller dwarf galaxies like the Sagittarius dwarf galaxy, tearing them apart and absorbing their stars and dark matter. The existence of dwarf galaxies, of spiral galaxies like our own, and the entire cosmic web of structures we see is overwhelming proof. This bottom-up formation is only possible if the invisible scaffolding was built from cold dark matter. If dark matter had been hot, the seeds for all these small galaxies would have been erased before they ever had a chance to grow. The universe would look completely different and we likely wouldn't be here to see it. The Great Confusion. So our detective sketch is now much clearer. The culprit must be cold, slow-moving dark, doesn't interact with light, and matter has gravity and clumps together. With this precise description, physicists turn to their suspect list, the complete list of all known proven particles in the universe. This list is called the Standard Model of Particle Physics. It's one of the most successful theories in all of science, describing every fundamental particle and force we've ever measured, from the electron to the photon to the Higgs boson. And this is where we hit a terrifying brick wall. We check the list. Is it the electron? No. It has an electric charge and interacts strongly with light. Is it the proton or neutron? No, that's regular baryonic matter. It makes stars and planets. It's not dark. Is it the photon? No, that is light. Is it the neutrino? No, it's hot. It fails at the cold test. Physicists went down the entire list of the 17 fundamental particles in the Standard Model. Not a single one of them matches the description. This is a profound, universe-shaking revelation. The Standard Model. The triumphant summary of a century of physics is incomplete. It only describes the particles that make up 5% of the cosmos, the regular matter. The other 27%, the cold, dark matter that holds our entire universe together, must be something else entirely. It must be a new particle, something that is not and has never been part of our standard theories. It points to new physics. We have a perfect description of a ghost, but we have absolutely no idea what kind of being it is. We know what it does, but we don't know what it is. This confusion is the single biggest mystery in modern physics, and it has launched a global hunt deep underground in particle colliders and in space telescopes to finally catch one of these invisible particles and complete the portrait of the deity of the universe. Now, as we stand in the shadow of this immense invisible cosmic web woven by dark matter, it's absolutely essential that we pause and address a common point of confusion. There is another dark entity in the universe, another profound mystery that often gets tangled up with dark matter in our minds. But they could not be more different. I'm talking about dark energy. Let's make a very important clarification right here, because understanding this difference is key to understanding the entire modern picture of the cosmos. Dark matter and dark energy are not related. They are two completely separate, distinct phenomena that are in fact locked in a cosmic battle for the ultimate fate of the universe. Think of it this way. If dark matter is the universe's great collector, its silent sculptor, then dark energy is its great disperser. Dark matter is the cosmic glue. Its only job, as far as we can tell, is to pull things together through gravity. It's the invisible mass that gathers hydrogen and helium gas into the first stars. It's the gravitational anchor that holds our Milky Way galaxy together, preventing stars like our Sun from being flung out into the void. It builds the structures. It is a force of attraction, of gathering, of creation. Dark energy, on the other hand, is the cosmic push. It is a mysterious pressure that exists in the very fabric of space-time itself. It doesn't clump together or form structures. Instead, it acts everywhere, uniformly as a repulsive force. It pushes everything away from everything else, working directly against gravity's pull. If dark matter is trying to build a beautiful house of cards, dark energy is the force trying to blow the table apart. The story of how we discovered this cosmic push is one of the most shocking and revolutionary tales in the history of science. It begins as in the late 19th. At the time, astronomers were engaged in a grand project to measure the precise history of our expanding universe. The Big Bang had set everything in motion, flinging all of space outwards. But everyone, and I mean everyone, expected that the expansion must be slowing down. It just made sense. The universe is filled with matter, stars, galaxies, and as they were beginning to fully appreciate a vast amount of dark matter, all of this matter has gravity, and gravity pulls things together. So like a ball thrown into the air, the universe should be slowing its ascent eventually to either hang in a delicate balance or come crashing back down in a big crunch. The only question astronomers had was, by how much is it slowing down? To figure this out, they needed a way to measure vast distances across space and time. They needed a standard candle, an object whose true brightness is so well known that you can tell its distance just by seeing how faint it appears to us. They found the perfect candle in a specific type of stellar explosion called a Type Ia supernova. These events are astonishingly reliable. They occur when a small dense star called a white dwarf, part of a binary star pair, siphons off material from its larger companion. It greedily pulls in more and more mass until it reaches a precise critical tipping point about 1.4 times the mass of our Sun. At that exact moment, it ignites in a cataclysmic thermonuclear explosion that can outshine its entire host galaxy for a few weeks. Because they all explode at the exact same mass, they all explode with the exact same peak brightness. They are cosmic light bulbs of a known wattage. So, two independent teams of astronomers set out to hunt for these supernovae in distant galaxies. By measuring their faintness, they could calculate their distance. By measuring their redshift, the stretching of their light as they speed away from us, they could calculate their speed. By putting these two pieces of information together for supernovae at many different distances, they could create a map of how the universe's expansion has changed over billions of years. As the data started to come in, something was deeply wrong. The most distant supernovae, the ones that showed us what the universe was doing billions of years ago, were consistently dimmer than they were supposed to be. They were fainter than the models predicted. There was only one possible and seemingly impossible explanation for this: they were farther away than they should be. The only way for them to be farther away was if the expansion of the universe hadn't been slowing down at all. In fact, for the last 5 to 6 billion years, the expansion has been speeding up. This was a discovery that shook the cosmology to its core. It was like throwing a ball into the air and watching it suddenly shoot upwards faster and faster into the sky. It defied everything we thought we knew. Some force, some unknown energy had to be overwhelming gravity on the largest of scales and pushing the universe apart at an ever-increasing rate. This unknown force was given the name dark energy. When we now do the accounting, when we create a budget for all the mass and energy in the entire universe, the picture that emerges is humbling, almost unbelievable. Everything we can see, everything we know, every star, planet, asteroid, comet, every black hole, every nebula, every human being, every grain of sand on every beach on Earth, all of that normal matter adds up to just under 5% of the universe. The invisible gravitational scaffolding, the dark matter that holds it all together, makes up about 27%. And the rest, roughly 68% of the entire cosmic budget, is dark energy. This mysterious anti-gravitational push that fills all of space. Let that sink in for a moment. All of human history, all of our science, our art, our conflicts, our love, our exploration of the world and the stars has been the study of a mere 5% of reality. We are living in a cosmos whose nature and destiny are overwhelmingly dominated by two dark components that we are only just beginning to acknowledge, let alone understand. We are in a very real sense strangers in our own universe, just waking up to the true nature of our home. It's a profoundly humbling realization, and it tells us that the greatest age of discovery may have only just begun. This leads us to the most popular idea, the particle hypothesis. The vast majority of physicists believe dark matter is not just normal matter we can't see, but an entirely new kind of particle, one that isn't part of our standard model of physics. The hunt is on to find it, and two candidates have dominated the search for decades. The first and most famous candidate is the WIMP, which stands for Weakly Interacting Massive Particle. WIMPs are predicted by a powerful theory called supersymmetry. This theory suggests that every particle we know has a heavier superpartner. The lightest of these superpartners would be stable heavy, and interact only through the weak force and gravity, making it a perfect WIMP and a perfect dark matter particle. What made WIMP so exciting was something called the WIMP miracle. When physicists calculated how many of these heavy particles would have been created in the fiery conditions of the Big Bang, and how many would be left over today, the answer was astonishing. The calculated amount matched the amount of dark matter we actually observe in the universe almost perfectly. It seemed too good to be a coincidence. This sparked a massive search effort. To find a WIMP, scientists built enormous, incredibly sensitive detectors. They buried these detectors deep underground, often in old mines or under mountains. This is crucial to shield the experiment from cosmic rays and other radiation from space that could create false signals. These detectors are essentially traps, often using huge tanks of purified liquid like xenon or ultra-cold crystals. The entire experiment waits in complete darkness and silence, listening for the tiniest bump. The idea is that while billions of WIMPs pass through you that hit Earth and the detector every second, very rarely, one WIMP might just happen to collide directly with the nucleus of one atom in the detector. This collision would cause a microscopic flash of light or a tiny vibration which the sensitive instruments are designed to pick up. The result of this decades-long hunt. A profound silence. Despite building bigger and more sensitive detectors and running them for years, not a single undeniable WIMP signal has ever been confirmed. This silence is a huge problem and has caused a crisis in the field. The WIMP miracle now looks less like a miracle and more like a frustrating coincidence. This has shifted attention to the second major candidate, the axion. The axion is the polar opposite of the WIMP. It is an extremely light particle, potentially billions or even trillions of times lighter than an electron. The axion wasn't invented for dark matter. It was proposed back in the 1970s to solve a completely different, very specific puzzle in particle physics known as the strong CP problem. It was only later that scientists realized that if actions exist, they would have been produced in enormous numbers in the Big Bang and could easily make up all the dark matter. Searching for actions requires completely different experiments. You can't wait for one to bump into an atom. They are far too light. Instead, experiments like the ADMX experiment use extremely powerful magnetic fields. The theory predicts that in the presence of a strong magnet, an action can sometimes convert into a tiny particle of light, a photon. The experiment is like a very sensitive radio, slowly tuning its dial through different frequencies, listening for the specific station, the photon signal, that would prove the axion is real. The result here. Still searching. Like with WIMPs, no axions have been found yet. However, the search is much younger than the WIMP hunt, and there are many frequencies left to check. This persistent silence from our two best candidates is forcing us to think again. It means our simplest, most elegant ideas about dark matter might be wrong, pushing scientists back to the drawing board to invent new theories and new, more creative ways to hunt for this invisible cosmic ghost. When we look up at the night sky, we see points of light, stars, galaxies, and clusters. We are by nature focused on the stuff we can see. It's natural to assume that this visible matter, which we call baryonic matter, is the star of the show. We might be tempted to think that dark matter, this invisible substance, is just some exotic minor ingredient sprinkled on top a bit of extra seasoning in the cosmic soup. This assumption is perhaps the most profound misunderstanding we could have about our universe. Dark matter is not an afterthought. It is not extra. It is the foundation. If the universe were a grand cathedral, the stars and galaxies we see are not the load-bearing columns. They are the stained glass windows, the beautiful art that was only installed after the true hidden structure was in place. Dark matter is the blueprint, the scaffolding, and the chief architect of all cosmic structure. Without it, the universe we inhabit would be impossible. It would be an empty, dark, and formless void. To understand why, we must go back to the very beginning. In the first few 100,000 years after the Big Bang, the universe was an unrecognizable place. It was not dark and cold, it was blindingly bright and unimaginably hot. It was a seething fog of plasma, a chaotic soup of fundamental particles like protons, electrons, and crucially photons, particles of light. In this early inferno, ordinary matter, the baryonic matter, was in a terrible bind. It had gravity and it wanted to clump together. Gravity was patiently trying to pull particles together to start building the first atoms, the first stars. But it was constantly defeated by another, more powerful force, radiation pressure. The photons, the particles of light, were so energetic and so numerous that they acted like a violent cosmic hurricane. Every time a proton and an electron tried to get together, a high-energy photon would slam into them, blasting them apart. Every time a small clump of gas tried to form this hurricane of light would blow it to bits. The universe was full of this photon-baryon fluid, where matter and light were coupled or stuck together. Gravity would pull and light pressure would push. The result was a cosmic stalemate. For ordinary matter, structure was impossible. But dark matter had a secret weapon. Its defining characteristic is that it does not interact with light. It is dark not because it is black, but because it is completely, utterly transparent. While ordinary matter was being tossed around in the photonic hurricane, the dark matter particles felt nothing. The photons passed right through them as if they weren't there. This meant that dark matter was immune to the radiation pressure that was paralyzing the rest of the universe. It was decoupled from the cosmic chaos. And so from the earliest moments after the Big Bang, dark matter began its work. Unhindered by the light storm, dark matter particles answered to only one master, gravity. Slowly, patiently, and relentlessly they began to clump together. While ordinary matter was held in suspension, dark matter began to form vast invisible concentrations. These were the seeds of everything to come. These massive, invisible clumps of dark matter exerted a powerful gravitational pull. They began to warp the fabric of space-time around them, creating what we call gravity wells. Imagine a flat, stretched rubber sheet. This is empty space. Now imagine scattering invisible heavy marbles across it. Each marble creates a dip, a well. This is what dark matter did to the universe. It created an invisible geography, a network of gravitational valleys, basins, and deep pits. Over hundreds of thousands of years, these wells grew deeper and deeper as more dark matter fell into them. They formed a vast invisible network spanning the entire cosmos, connecting in long filaments and clustering at massive nodes. This is the cosmic web that forms the skeleton of our universe. Dark matter was the architect, and it had built the scaffolding. All this time, ordinary matter could only watch, still trapped in its struggle with the light. Then, in about 380,000 years after the Big Bang, the universe reached a critical turning point. The cosmic expansion had cooled the universe enough for a miracle to happen. The photons in the hurricane finally lost enough energy. They were no longer strong enough to blast atoms apart. In a moment of cosmic transition, the electrons were finally captured by the protons, forming the first stable neutral atoms of hydrogen and helium. This event is called recombination. When this happened, the universe fundamentally changed. The photons, which had been trapped by bouncing off free electrons, were suddenly set free. The fog cleared. The universe for the first time became transparent. This first light set free is what we now detect as the cosmic microwave background radiation. But for matter, the most important consequence was this: the hurricane stopped. The radiation pressure that had held ordinary matter hostage simply vanished. Suddenly, for the first time, this ordinary gas was free to move, and it was now dominated by one single force: gravity. Where did it go? It fell. Like rain falling from the sky and collecting in valleys and lakes, the ordinary gas began to stream across the cosmos, pulled inexorably toward the deepest gravitational points it could find. And what had created these deep points? The massive invisible gravity wells that dark matter had been patiently dredging for the past 380,000 years. The ordinary matter fell into these pre-built invisible molds. The dark matter scaffolding, the gravity wells, acted as giant basins collecting all the gas from the surrounding regions. As this gas poured into the dark matter halos, it was compressed, heated up, and began to churn. In the dense centers of these dark matter wells, the gas became so compressed that it ignited and the first stars were born. These were the first galaxies. Without dark matter, this never would have happened. The gravity of ordinary matter alone is far too weak. If the universe only contained the matter, we see its own feeble gravity would have been completely overwhelmed by the universe's expansion. The small random clumps that did form would have been too small and too diffuse. They would have been ripped apart by the accelerating expansion of space long before they could ever form a star. A universe without dark matter is a universe without structure. It would be a thin, cold, homogeneous, and utterly lifeless fog of hydrogen and helium growing ever thinner for all eternity. There would be no galaxies, there would be no stars, there would be no planets, and therefore there would be no us. Dark matter is not just a statistical anomaly or a physicist's curiosity. It is the architect of the cosmos. It is the invisible foundation upon which our galaxy was built. It is the silent sculptor that carved the gravity wells that became our home. We are here able to wonder about the universe only because this invisible nothing provided the framework for something. The power of a digital universe. To understand why computers are one of the most powerful tools in the search for dark matter, we have to think about the problem of scale. We cannot build a galaxy in a laboratory. We cannot travel to the edge of the universe to see how it is put together. And most importantly, we cannot press fast forward on the real world to watch the 13.8 billion-year story of cosmic evolution unfold. Our human lives are just a single frame in a movie that is billions of years long. This is where supercomputer simulations come in. A simulation is in essence a digital universe in a box. Scientists use these simulations as a cosmic laboratory to test their ideas. The process is a bit like baking a cake, but on a cosmic scale. First, you need a recipe. This recipe includes two things: the ingredients and the rules. The ingredients are the different stuffs that make up the universe: normal matter, like hydrogen and helium gaslight, and if your theory includes it, dark matter. The rules are the laws of physics, most importantly the law of gravity. Gravity is the engine that assembles everything. To start the simulation, scientists input the starting conditions. We actually have a very good snapshot of these conditions from our observations of the cosmic microwave background, the leftover heat from the Big Bang. This snapshot shows us a baby universe that was incredibly hot dense and almost perfectly smooth. There were only tiny microscopic differences in density from one place to another. The simulation begins with this smooth, hot digital baby universe. Then the scientists press run. The supercomputer then calculates the force of gravity between all the particles in the box, moves them a tiny bit, and recalculates over and over again. It does this millions and millions of times, allowing this digital universe to grow up, expand, and evolve over a virtual 13.8 billion years. The whole point of this massive calculation is to ask one simple question. At the end of the simulation, does our digital universe look like the real universe we see outside our window? If we point a virtual telescope at our simulated cosmos, does it have the same number of galaxies clustered in the same way as the real night sky? If the final picture does not match reality, it means our recipe was wrong. We used the wrong ingredients. If it does match, it gives us huge confidence that our list of ingredients is correct. The no dark matter experiment. So the first and most obvious test to run is this. Let's try to build a universe using only the stuff we can see. This is the no dark matter simulation. Scientists programmed the supercomputer with all the known laws of gravity. For the ingredients they put in only normal matter, the 5% of the universe that is made of atoms, hydrogen, helium, and all the elements on the periodic table that make up stars, planets, and us. They did not add any dark matter to this recipe. They set the simulation to run starting from the smooth conditions of the early universe. The computer calculated the evolution of this normal matter-only universe for billions of virtual years. The result was a complete failure. In this simulation, gravity did pull the normal matter together. Some small structures and a few galaxies did manage to form, but because there was so little matter, only 5%, there was simply not enough gravity to get the job done. The universe's expansion, which constantly pulls everything apart, easily overpowered the weak gravitational pull of this small amount of matter. The final picture was a universe that looked nothing like our own. It was relatively flat, empty, and lifeless. It failed to form the massive galaxies we see, and it completely failed to form the gigantic clusters of galaxies that are the cities of our cosmos. Most importantly, it did not create any large-scale structure. It was a universe without a skeleton. This failure was not a small error. It was a clear and profound message: you cannot build the universe we live in using only normal matter. The recipe is wrong. A critical ingredient is missing. With dark experiment. Now scientists tried again. This time they used the full recipe proposed by the current theory known as the lambda cold dark matter model. They started with the same laws of gravity and the same 5% of normal matter, but this time they added the missing ingredient. They told the computer to include a second type of stuff which had a very specific set of properties. It is dark. It does not interact with light in any way. It is completely invisible. It has gravity, it has mass, and it pulls on other thing, and is pulled on through gravity. It is cold. This is the key detail. Cold just means it moves slowly. It is not zipping around at high speed. Because it is slow, it can clump together easily. There is a lot of it. Based on other observations like the cosmic microwave background, the simulation added about 5 times more of this cold dark matter than normal matter. So this new recipe was 5% normal matter, 25% cold dark matter, and the rest 70% as dark energy, which drives the expansion. They hit run on this new simulation. What emerged was a revelation. From the very beginning, this new ingredient changed everything. Because there was so much dark matter, its gravity dominated the baby universe. While the normal matter was being pushed around by light and pressure, the cold dark matter was not. It immediately began to clump together under its own gravity. These tiny clumps of dark matter acted as seeds. They created little pools of gravity called dark matter halos. As the universe expanded, these halos grew, pulling in more dark matter and creating an enormous invisible scaffolding for the cosmos. The normal matter, the hydrogen and helium gas, felt the gravitational pull from this invisible scaffolding. The gas began to fall into these pre-made dark matter halos like water flowing into the deepest valleys. The dark matter formed the mold, and the normal matter was the material that filled it. As the simulation fast-forwarded through billions of years, this structure grew more and more complex. The dark matter formed long, massive strands and filaments connecting dense, heavy junctions. Inside the densest halos, the normal matter gas collapsed, cooled and ignited into stars, forming the galaxies we see. These galaxies then surfed along the invisible filaments, streaming towards the massive junctions. These junctions, the crossroads of the cosmic highway, became the galaxy clusters, massive collections of thousands of galaxies all trapped in a single enormous cloud of dark matter. The vast regions between the filaments where the dark matter was thinnest became the cosmic voids, immense, dark and empty regions of space. When the simulation finished, the scientists looked at the final image. It was a perfect, stunning reproduction of the real universe. It showed a vast, beautiful web-like structure, the cosmic web. When they compared the statistics of this simulated web to the maps of real galaxies from our telescopes, the match was exact. The number of clusters, the size of the voids, the stringiness of the filaments, everything was right. The verdict from the machine: This is the central pillar of evidence from computer simulations. It is indirect evidence, but it is incredibly strong. We ran 2 experiments in our digital laboratory. Universe A, no dark matter. This simulation failed, producing an empty, structureless cosmos. Universe B, with cold dark matter. This simulation succeeded, perfectly reproducing the cosmic web, the clusters and the galaxies we observe in reality. The simple and unavoidable conclusion is that our universe must contain this invisible, slow-moving gravitational scaffolding. Without it, we simply cannot explain the structure we see. The fact that adding this one ingredient makes the simulation work is one of the most profound and convincing arguments that dark matter is real. The cold dark matter model is without a doubt one of the most successful theories in modern science. It acts as the backbone of our entire understanding of cosmology. On the grandest scales, it explains everything we see: the vast sponge-like cosmic web, the way galaxies cluster together, and even the patterns of light left over from the Big Bang. The agreement between the model's predictions and our observations of the large-scale universe is breathtakingly precise. But there's always a but, and in cosmology the but gets louder the closer you look. While cold dark matter, or CDM, is a champion at explaining the big picture, it begins to stumble when we zoom into the smallest scales, specifically the scales of individual galaxies and their local neighborhoods. This disconnect is known as the small-scale crisis, a collection of persistent nagging problems that suggest the simple, elegant picture of CDM might be incomplete. The very nature of cold dark matter is the source of its predictions. Cold means the particles were moving very slowly in the early universe. Because they were slow, they were incredibly good at clumping together. Gravity could easily grab them and pull them into structures. A key prediction of this model, therefore, is that the universe should be clumpy at all levels. Our most powerful computer simulations built on the rules of CDM show this clearly. They produce a cosmic web filled with massive halos, which are themselves filled with medium halos, which are in turn filled with thousands of tiny small halos. The problem arises when we compare this bottom-up clumpy simulation to the universe we actually live in. The first major crack is called the missing satellites problem. Our simulations of a galaxy like the Milky Way are very clear. Our home galaxy should be sitting within a massive dark matter halo, and that halo should be swarming with a huge number of smaller subhalos, each containing its own dwarf satellite galaxy. The simulations consistently predict that a galaxy our size should be orbited by hundreds, perhaps even thousands of these small companions. When we look up at the sky, we do see satellite galaxies. The large and small Magellanic Clouds are the most famous examples. For decades, however, we could only find about a dozen of them. The simulations predicted hundreds, we saw 12. This was a massive discrepancy. Where were all the others? In recent years, new powerful telescopes have scanned the skies with greater sensitivity, and they have found more. We have now catalogued several dozen ultra-faint dwarf galaxies orbiting the Milky Way. This discovery has eased the tension, but it hasn't completely solved it. The numbers still don't quite match, and it has forced astronomers to ask new questions. Are the missing satellites simply too dark for us to see, having failed to form any stars? Or did the dark matter halos they were supposed to live in never form in the first place? This leads directly to the second major issue, the cusp core problem. This problem looks at the internal structure of the dark matter halos themselves. Let's go back to those computer simulations. Because the cold dark matter particles are slow and only interact with gravity, they relentlessly fall toward the center of their own halo. Over billions of years, the simulations show the density of dark matter should skyrocket as you approach the very center. It should form a sharp, dense spike. Astronomers call this a cusp, like the sharp, pointy peak of a mountain. The CDM model is adamant the centers of dark matter halos must be cuspy. But our observations tell a different story. We can't see this dark matter directly, but we can measure its gravitational pull by watching the orbits of stars inside these galaxies. When we do this, especially in dwarf galaxies, which are almost entirely dark matter, making them perfect laboratories, we don't find a cusp. Instead, we find that the density of dark matter flattens out near the center. It's more like a core, a rounded plateau, or a flat-topped hill. This is a fundamental conflict. Our simulations demand a sharp, dense cusp. Our observations show a fluffy, broad core. These two problems, not enough small galaxies and the ones we do see having the wrong shape, have sent theorists scrambling for an answer. And one of the most popular candidates completely changes the central assumption of the model. What if the dark matter isn't cold? What if it's warm? This introduces a new character to our cosmic story, warm dark matter, or WDM. This is a hypothetical particle that sits in a Goldilocks zone of speed. Hot dark matter HDM particles like neutrinos moved at nearly the speed of light. They were too fast for gravity to ever catch, so they would have wiped out all but the largest structures. We already know this is wrong because galaxies like ours exist. Cold dark matter. CDM particles moved very slowly, allowing them to clump together at every possible scale. Warm dark matter, WDM particles, would have been moving at a medium speed. They were zippy, but not too zippy. This one simple change in velocity has profound consequences. In the early universe, these zippy WDM particles could run away from the smallest gravitational traps. Their own motion would allow them to stream freely, washing out or erasing the smallest scale structures before they ever had a chance to grow. This single idea offers a beautiful solution to both small-scale problems at once. How does it solve the missing satellites problem easily? Warm dark matter predicts that the smallest dark matter halos simply never formed. They were smoothed out of existence by the particle's own motion. If the smallest halos never existed, then no dwarf galaxies could form inside them. The satellites aren't missing, they were never born. How does it solve the cusp core problem? Again, the particle's motion provides the answer. Unlike cold particles, which can fall passively to the center and pile up, warm particles are always in motion. They can't be packed down into an infinitely dense point. Their inherent zippiness creates a natural buffer, a kind of pressure that resists extreme compression. This naturally smooths out the center of the halo, creating the exact kind of flat core that our observations seem to show. It sounds like a perfect solution. So is that the answer? Have we replaced CDM with WDM? Not so fast, the debate is on from over. Warm dark matter is an elegant solution, but it has its own issues. Some models show that if you make the particles warm enough to solve the small-scale problems, they start creating new problems on larger scales, like preventing galaxies from forming as early as we see them. Furthermore, there is another solution, one that saves the original cold dark matter model. What if the dark matter is perfectly cold, but our simulations are missing a crucial ingredient? The messy, violent physics of normal matter. We've been talking about dark matter as if it exists in a dark, quiet universe. But it shares that universe with stars, gas, and black holes. Perhaps the cusp core problem isn't a dark matter problem at all. Maybe when the first stars in a dwarf galaxy are born, they explode as supernovae. Perhaps those repeated powerful explosions, a process called baryonic feedback, can physically kick the dark matter, blasting it out from the center and smoothing the cusp into a core. In this scenario, the dark matter wants to form a cusp, but the normal matter living inside it just won't let it. This is where cosmology stands today. The beautiful, simple model of cold dark matter has developed a few cracks. These cracks are not a sign of failure. They are the most exciting clues we have. They point to a deeper, more complex reality. The answer likely lies in one of two directions. Either the dark matter particle itself is more complex than we thought, perhaps it's warm, or the dark matter is simple, but its dance with the bright, messy normal matter that makes up our world is far more intricate than we ever imagined. If we can't catch the particle itself, perhaps we can define the footprints it leaves behind. This is the entire philosophy behind indirect detection. We stop trying to catch the single elusive dark matter particle hitting a detector here on Earth, and instead we use our most powerful telescopes to look for the evidence of dark matter operating on a massive cosmic scale. This approach generally follows two main lines of thought. The first is annihilation. Many theories, especially those involving WIMPs, weakly interacting. Massive particles suggest that dark matter is its own antiparticle. This means that when two dark matter particles collide, which should happen frequently in a place crowded with dark matter like the center of our galaxy, they would annihilate each other. They would vanish in a flash of pure energy, converting all their mass into new particles we can see. This cosmic explosion would shoot out high-energy gamma rays, neutrinos, and even antimatter particles like positrons. The second idea is decay. What if dark matter isn't perfectly still? What if over the immense timescales of the universe, the dark matter particle slowly falls apart? If this were happening, it would also release a steady stream of energetic particles. So the strategy is simple: point our best telescopes at the densest regions of dark matter we know and look for an excess of these signals. We search for a glow of gamma rays or a flood of positrons that cannot be explained by any normal known astronomical objects. We look for the echo of dark matter's presence. For years, this search has given us tantalizing hints, moments where astronomers thought, this is it, we've found it. but every single time these hints have remained frustratingly ambiguous. The most famous of these is the galactic center excess seen by the Fermi Gamma Ray Space Telescope. Fermi scans the entire sky, mapping the most violent and energetic light in the universe. When it looked toward the very heart of the Milky Way, it found a mysterious spherical glow of gamma rays. This glow was exactly what scientists predicted dark matter annihilation would look like. The signal was strong and its energy profile was a perfect match for many WIMP theories. For a while it was the best lead we had. But the universe is a messy place. The center of our galaxy is also filled with other objects that create gamma rays. The most likely culprit, pulsars. These are incredibly dense dead stars that spin hundreds of times per second, sweeping beams of energy across the cosmos like cosmic lighthouses. Many scientists now argue that this excess glow isn't dark matter at all, but rather the combined faint light of thousands of undiscovered pulsars that our telescopes just aren't sharp enough to see individually. The data can be explained by both, and we have no way to be certain. Then there is the positron excess. A detector mounted on the International Space Station, the Alpha Magnetic Spectrometer, or AMS-2, was built to catch high-energy particles from space known as cosmic rays. It's like a particle detector in orbit. One of its key findings was that it detected too many positrons, the antimatter version of the electron. Just like with the Fermi glow, this was another eureka moment. Positrons are a predicted byproduct of dark matter annihilation or decay. This excess of antimatter coming from all directions seemed to be a powerful signature. But once again there was a mundane explanation: those very same pulsars. Pulsars are surrounded by incredibly powerful magnetic fields that are more than capable of creating pairs of electrons and positrons and flinging them across the galaxy. It is entirely possible that the extra positrons AMS-2 is seeing are just the exhaust from a few relatively nearby pulsars. Finally, there is the most specific signal of all the mysterious 3.5 keV line. This was different. It wasn't a broad glow, it was a single razor-thin spike of energy, like hearing one specific faint musical note in a sea of cosmic static. This X-ray signal was seen faintly in distant galaxy clusters. A spike like this is the classic sign of a particle decaying, because a decay would always release the exact same amount of energy. This got many people excited, especially supporters of a theory involving a sterile neutrino decaying. But the signal is incredibly weak, right on the edge of what our instruments can even detect. Some analyses don't see it at all, and even if it's real, it could be a weird atomic process we just don't understand yet. All of these signals suffer from the same problem. They are all unclear. They are echoes in a canyon already filled with noise. This ambiguity has forced us to ask a much stranger question. What if we've been looking for the wrong thing entirely? We've assumed dark matter is a new microscopic particle, but what if it's something big and something we already know exists? This is the strange and compelling idea of primordial black holes, or PBHs. What if dark matter is not a particle at all, but a countless number of black holes that were formed in the very first second of the universe's existence? We know that black holes are dark, they trap light and have mass, they exert gravity. They fit the description perfectly. These wouldn't be the black holes we know, which form when a massive star dies and collapses. These primordial black holes would have formed in the chaotic, ultra-dense soup of energy just moments after the Big Bang. In that first instant, some regions of the soup might have been so incredibly dense that they collapsed under their own gravity, forming black holes before the first atoms even existed. This idea was largely considered a fringe theory for decades, but it saw a stunning revival recently thanks to the LIGO Gravitational Wave Observatory. LIGO hears the universe shake when black holes collide, and in 2015 it began detecting these collisions. The surprise was the size of the black holes. They were in a strange weight class around 30 times the mass of our Sun. This was heavier than astronomers expected most star-based black holes to be, but much lighter than the supermassive black holes at the centers of galaxies. Suddenly, scientists asked, where did these strange mid-sized black holes come from? The discovery opened the door for the primordial black hole idea to come rushing back in. What if these LIGO detections are the first glimpse of this ancient hidden population? What if the universe is teeming with them, and they are the missing mass? This possibility remains one of the most fascinating and mind-bending alternatives in all of cosmology. While our observations of things like gravitational lensing, how gravity bends light, place very strict limits on how many black holes of certain sizes can be out there, the possibility is not zero. The dark matter that holds our galaxy together might not be a ghostly invisible particle, but a swarm of the oldest, darkest objects in the universe. it remains an incredibly attractive possibility left wide open for discovery. When we look for the most powerful, undeniable proof for dark matter, we look back in time. We look to the very first light that was ever set free in the universe. This evidence is called the cosmic microwave background, or the CMB. It is the bedrock of our understanding, a baby picture of the cosmos taken when it was only 380,000 years old. This picture isn't of stars or galaxies because they hadn't formed yet. Instead, it's a snapshot of a moment in time, the moment the universe, which had been a hot, dense, opaque fog, suddenly became transparent. Before this moment, the universe was a scorching hot soup of fundamental particles. Protons, electrons, and photons, particles of light, were all mixed together in a state called a plasma. Light couldn't travel freely. A photon would move a tiny distance, crash into an electron, and scatter. The entire universe was a glowing, impenetrable fog. In this primordial soup, a massive battle was underway. Two great forces were pushing and pulling on all the normal matter, which scientists call baryons. The first force was gravity. Gravity wanted to pull everything together, to collapse the matter into dense clumps. The second force was radiation pressure. The flood of photons trapped in the soup acted like a powerful pressure washer, pushing outward against any clump of matter that tried to form. This cosmic tug-of-war gravity pulling in light pressure pushing out created massive vibrations that rippled through the plasma. These were quite literally sound waves. Just like sound waves in the air are regions of compressed air and spread out rarefied air. These cosmic sound waves were regions of compressed hot plasma and rarefied cooler plasma. These sound waves sloshed back and forth for hundreds of thousands of years. Then, when the universe reached the age of 380,000 years, it cooled down enough for electrons to finally stick to protons, forming the first stable neutral hydrogen atoms. This event is called recombination. Suddenly the fog cleared. The photons, which had been trapped and scattered by the free-floating electrons, were now free to travel. They burst out in all directions, suddenly released from the plasma. The light that was released at that exact moment has been travelling across the universe ever since for 13.8 billion years. When we detect it today, we see the CMB. The crucial part is that this light carries the fingerprint of those last moments. The map of the CMB, which we have painstakingly created with satellites like Planck, shows a pattern of tiny temperature differences. We see hot spots and cold spots. These are not mistakes. They are the frozen echoes of those ancient sound waves. The hot spots are where the plasma was compressed and dense when the light was set free. The cold spots are where the plasma was spread out and thin. This is where dark matter enters the story, and it does so in a way that is mathematically unavoidable. Dark matter has one property that makes it completely different from the normal matter in the plasma soup. Dark matter does not interact with light. It does not feel the push of radiation pressure. It only feels the pull of gravity. So while the normal matter, protons and electrons, was being sloshed back and forth by gravity and light pressure, the dark matter was doing something else. It was only responding to gravity. It began to clump together quietly in wells of gravity, creating pools of invisible mass. The normal matter would then fall into these gravity wells, but because it did feel the light pressure, it would be blasted back out only to be pulled back in again. Think of it like this. Imagine a swimming pool. The water is the normal matter, and the photons are creating waves, sloshing the water back and forth. But now imagine there are heavy, invisible boulders sitting at the bottom of the pool. The boulders are the dark matter. The water waves, the sound waves, are affected by the shape of the pool bottom. The water will splash higher and behave differently, because those boulders are there even though the boulders themselves aren't moving with the waves. The dark matter boulders change the sound of the cosmic waves. They provided extra gravitational pull. They made the gravity wells deeper. When scientists analyze the CMB map, they don't just look at the spots. They perform a mathematical analysis of how many spots there are of each specific size. This analysis creates a graph called the power spectrum. This graph is the fingerprint of the universe's ingredients. The power spectrum graph shows a series of peaks. These acoustic peaks tell us the precise nature of the sound waves. The first biggest peak tells us the fundamental note of the universe, which confirms its overall geometry. It is flat. But the other peaks, specifically the second and third peaks, are the smoking gun. The relative heights of these peaks tell us exactly what the plasma was made of. The second peak is related to the rebound, the rarefaction, while the third peak is related to the next compression. The height of the second peak tells us with incredible precision the total amount of normal matter baryons in the universe. The height of the third peak is the key. Its height relative to the first two is dictated by the total amount of matter, including the matter that doesn't get pushed around by light. It measures the matter that was just sitting in the gravity wells, adding its pull the dark matter. When scientists built computer models of the early universe, they tried to create a power spectrum that matched the one we actually see. If they built a model with no dark matter, the graph looked completely wrong. The peaks were all the wrong heights. The sound was totally different. If they built a model with only normal matter, the gravity would not have been strong enough to create the structures we see. The only way to make the model perfectly match the data measured by the Planck satellite to get every peak and every valley in the graph exactly right was to set the ingredients to very specific values. The model only works if the universe is made of approximately 5% normal matter, about 25% dark matter, and the rest dark energy. This precision is breathtaking. The data from the Planck satellite confirms this number to a tiny fraction of a percent. This isn't a theory, it is a measurement. The CMB proves that 25% of the universe's mass energy budget was already in the form of a non-interactive invisible substance just 380,000 years after the Big Bang. It was the gravitational scaffold already in place waiting for the normal matter to settle in, and one day form the galaxies we see today. We find ourselves at a critical junction in this cosmic detective story. For decades we have operated on one primary assumption, that our understanding of gravity as laid out by Isaac Newton and Albert Einstein is correct. Because this assumption is so strong, the only way to explain the universe, we see the high-speed spinning of galaxies, the bending of light around invisible objects, the very structure of the cosmos, is to invent a new substance. We call this substance dark matter, an invisible ghostly material that makes up more than 80% of all matter in the universe. We have built our entire standard model of cosmology on the foundation of this invisible stuff. We are hunting for it in deep underground mines, smashing particles together in colliders, and scanning the skies all in an attempt to prove its existence. But what if we are wrong? This is perhaps the most profound and radical question in all of physics. What if the solution isn't to invent a new invisible particle? What if the problem isn't with the matter at all, but with our understanding of the force? What if there is no dark matter, and the reason galaxies are spinning too fast is simply because our theory of gravity is incomplete? This startling idea is the basis for a theory known as MOND, which stands for Modified Newtonian Dynamics. It was first proposed in the early 1980s by an Israeli physicist named Mordechai Milgrom. He looked at the data and saw a pattern that everyone else had missed. The discrepancy, the moment where observations flew in the face of theory, always happened in the same place at the very outer edges of galaxies. What is special about the outer edges? There is very little stuff out there. The stars are few and far between, and they are enormous distances from the gravitational centre of the galaxy. This means the pull of gravity they experience is incredibly, almost unimaginably weak. The acceleration of these stars, the rate at which they are being pulled toward the centre, is millions of times weaker than the acceleration you feel from Earth's gravity just sitting in your chair. Milgrom's hypothesis was revolutionary. He suggested that Newton's and Einstein's laws of gravity are perfect in high acceleration environments. Here in our solar system where the sun's gravity is powerful, or here on Earth, the theories work perfectly. But he proposed when acceleration drops below a certain tiny critical value, the rules of gravity itself change. He suggested that at these extremely low accelerations, gravity doesn't fade away as quickly as Newton predicted. Instead, it becomes stronger. It's as if gravity gets a boost when it becomes very weak, giving it a longer reach and a more powerful grip than we expected. For those stars on the edge of a galaxy, this modified stronger gravity would be just enough to grab them and swing them around at high speed. The mystery of the fast-spinning stars was solved. They aren't being pulled by invisible matter. They are being pulled by a different, stronger version of gravity itself. The reason MOND wasn't immediately dismissed as a wild fantasy is that it worked. It worked astonishingly well. This is MOND's incredible success. When proponents of the dark matter model try to explain a galaxy's rotation, they have to carefully build a custom halo of invisible dark matter around it. They have to tweak the size and shape of that halo until the simulation matches the observation. For many critics, this feels less like a prediction and more like forcing the data to fit the theory. MOND was different. It had one single simple rule change, and with that one rule it could take the visible matter of a galaxy, the stars and gas we can see, and predict its rotation curve almost perfectly, time and time again. No dark matter was needed at all. It explained a confusing observation known as the Tully-Fisher relation. which shows a direct link between a galaxy's brightness, its visible matter, and its rotation speed. In the Mond theory, this makes perfect sense. The speed is determined only by the visible matter because that's all there is. For the standard dark matter model, this relationship is a strange coincidence that needs a complex explanation. For explaining the dynamics of individual galaxies, Mond was a spectacular triumph. It was elegant simple, and it made predictions that held true. But if a theory is going to challenge Einstein, it can't just work in one specific area. It has to work everywhere. It has to explain not just galaxies, but the entire universe. And this is where Mond faces its great failure. The theory was a champion on the galactic scale, but it falls apart on the cosmic scale. The single most devastating piece of evidence against Mond is the bullet cluster. As we've discussed, this is the violent aftermath of two galaxy clusters colliding. When they passed through each other, the visible matter, the hot gas, crashed together in the middle. But gravitational lensing, the bending of light, showed that the gravity kept on going. The gravity and the visible matter were physically separated. Dark matter theory explains this perfectly. The invisible dark matter halos which don't interact passed through each other, like ghosts carrying their gravity with them. Mond has no answer for this. In Mond, gravity should only come from the visible matter. The centre of gravity should have stayed right there in the middle, with the hot gas, but it didn't. The bullet cluster seems to be a smoking gun proof that an invisible, non-interacting form of matter is real. And it gets even worse. Mond in its original form completely fails to explain the cosmic microwave background CMB. This map of the baby universe with its precise pattern of hot and cold spots is the blueprint for all of cosmic structure. The standard dark matter model predicts the exact size and distribution of these spots with breathtaking accuracy. Those patterns tell us the recipe of the early universe and prove that we needed a large amount of slow-moving, non-baryonic, non-normal matter to act as the scaffolding for galaxies to form. Mond provides no such scaffolding. It cannot explain how we got from that smooth early universe to the clumpy, complex web of galaxies we see today. This leaves us in a strange and fascinating place. Mond is a theory that is almost certainly wrong, yet it is also too good to be a complete coincidence. Its ability to perfectly predict galaxy rotation curves from visible matter alone is a mystery that the dark matter model still struggles to explain. Perhaps Mond is not the final theory but a symptom. It may be an important clue, a signpost pointing us toward a much deeper truth. It might be telling us that our understanding of gravity is incomplete, just not in the simple way Mond first proposed. Many physicists now wonder if this entire problem, the dark matter hunt, the strange success of Mendy, is hinting at the final frontier of physics quantum gravity. We have two pillars of science, general relativity for the very big and quantum mechanics for the very small. These two theories are incompatible. They do not work together. We know there must be a more profound theory, a theory of everything that unites them. Perhaps gravity is not a fundamental force at all, but an emergent property of something deeper happening at the quantum level. And maybe Mond is the first blurry glimpse of how that quantum level gravity behaves on the vast empty scales of a galaxy's edge. The mystery, it seems, is far from over. Our journey began in a place that felt familiar with a problem that seemed manageable. We looked at a star, a galaxy, and saw something that didn't fit our equations. We saw a collection of stars spinning far too quickly, moving with a velocity that should have torn them apart, flinging them into the cosmic emptiness. This single observation, this one anomaly, acted like a loose thread on the grand tapestry of the cosmos. We pulled it gently at first, expecting to find a simple knot, perhaps a mistake in our measurements or a slight miss under a request to translate the model's response to English. It seems the model's response is in English, but the user's request is in Vietnamese. I should confirm the user's intent. The user requested the text to be in English. The prompt is in Vietnamese, but the instructions are Hey ket thuk Viet cho to bang ting ang. I have correctly followed the instruction. The output should be in English. I will proceed with the original plan. The user has provided Vietnamese headings, but has explicitly asked for the final text to be in English. I must not write the headings. I must integrate their concepts. I must write in easy-to-understand English. I must write out any scientific symbols, e.g. percent instead of percent. I must aim for approximately 1,000 words. Here is the text. Our journey began in a place that felt familiar with a problem that seemed manageable. We looked at a galaxy and saw something that didn't fit our equations. We saw stars on its outer edges spinning far too quickly, moving with a velocity that should have torn them from their cosmic dance and flung them into the void. This single observation, this one anomaly, acted like a loose thread on the grand tapestry of our reality. We pulled it gently at first, expecting to find a simple knot, perhaps a mistake in our calculations of gravity, or a misunderstanding of the matter we could see. But the thread kept coming. As we pulled, our entire understanding of the universe began to unravel. What started as a puzzle about a spinning star became a profound interrogation of everything. We were forced to question the very nature of substance, the fundamental laws of gravity, and ultimately our own place in the cosmos. We were confronted with a staggering realization the matter we know, the stuff that makes up the stars, the planets, you and me, is almost nothing. It is a cosmic footnote, a rounding error. We have arrived at a point in our history where our most advanced science confidently tells us that we are ignorant of 95% of the universe. This is not a small gap in our knowledge. It is a chasm. The cosmos we have studied for millennia, the pinpricks of light in the night sky, are merely the foam on the surface of an ocean so vast and deep it defies our comprehension. We are explorers who have just realized we have been mapping a single tiny island, believing it was the entire world, while an unseen continent looms just beyond the fog. This realization transforms our view of existence. We do not simply live in a universe that contains this invisible substance. We live in a universe that is fundamentally defined by it. This unseen 95%, this dark matter and dark energy, is not a passive background. It is the architect. The normal matter we see is like paint, but this invisible substance is the scaffolding, the foundation, and the very structure of the house. It is the silent hand that shaped the cosmos from the chaos of the Big Bang. Without its immense gravitational pull, there would be no scaffolding. Without that scaffolding, the little wisps of hydrogen and helium we call normal matter would never have gathered. They would have remained a thin uniform soup adrift forever. This means that everything we cherish, every star, every planet, every molecule of water, and every living being owes its existence to this shadow. The dark matter acted as the gravitational seed, the cosmic anchor that allowed our matter to coalesce, to clump together, to ignite into stars. Those stars then forged the heavier elements, the carbon, the oxygen, the iron, and scattered them into space. Those elements formed new stars, new planets, and on at least one small blue world they formed life. Our reality is not just in a universe shaped by the invisible. Our reality is a consequence of it. We are held together, our galaxy is held together, and the entire cosmic web of superclusters is woven together by a thread we cannot see, touch, or yet understand. And so we build our traps. We have gone deep underground into mines and beneath mountains to shield our detectors from the constant noise of cosmic rays, the chatter of our own world. We have built extraordinary machines of immense sensitivity using exotic crystals and vast tanks of purified liquid, all designed to catch just one single particle of this dark matter as it passes harmlessly through the earth, through our bodies, through the detector itself. We have waited listening in the absolute dark, and the primary sound we have heard is silence. This silence from our detectors is perhaps the most profound message of all. In science, silence is not failure. It is not an empty void. It is data. It is the universe speaking to us in a subtle and challenging language. Every experiment that comes back empty is not a loss. It is a vital piece of the puzzle. It tells us what dark matter is not. It rules out our simplest, most hopeful theories. It tells us that the particle we were looking for, the one we thought was the most likely candidate, is either far more elusive than we imagined, or it is not there at draft. All. This silence forces us to be more creative. It pushes us back to the drawing board, compelling us to question our most basic assumptions. It tells us that the mystery is deeper, more complex, and perhaps more beautiful than we ever dared to believe. The universe is not giving up its greatest secret easily, and in its refusal it is teaching us the true nature of scientific inquiry. It is not about finding what we expect, but about having the courage to face what we find. This journey from a simple spinning star to the profound silence of our deepest laboratories brings us to a final gentle reflection on our own existence. We are the products of a process that this invisible shadow initiated. We are fashioned from the 5% of the cosmos that was allowed to gather, to burn, to live, and to think, all under the guidance of this silent, unseen majority. And now we, the small luminous part of the universe, have turned our senses back toward the darkness. We are the universe's way of becoming aware of itself. We are the cosmos's method of perceiving its own vast hidden shadow. There is a strange and beautiful symmetry in this. We are built from stardust, which itself was only possible because of the gravitational embrace of dark matter. Now this stardust has arranged itself into conscious beings, who build instruments to search for the very thing that made their existence possible. We are the universe reflecting upon its own structure. We are its self-awareness born from the light now peering into the dark. This silent connection, this link between our tangible bodies and the invisible scaffolding of reality, is the very definition of our place in the universe. We are not separate from this great mystery. We are its most complex and inquisitive expression, and our quest to understand it is in the end nothing less than the universe's quest to understand itself.